There is nothing that requires attention right now. Whatever the day held, its noise, its pace, its unfinished edges, none of it needs to be carried any further tonight. The body can remain exactly where it is. The mind does not need to go anywhere. There is only this narration, and even that can be allowed to drift, the way sound moves through a quiet room when no one is listening for it. Tonight, the only destination is a very small one, not a city, not a landscape, a kitchen counter late at night when the light is low and nothing is moving. On that counter, two small dishes sit side by side. In one, a scattering of white grains, dense and angular, catching whatever dim light reaches them. In the other, a second scattering of white grains, slightly larger, slightly rougher at the edges, glinting differently, not like polished stone, but like shattered glass held gently. Both are white, both are crystalline, and both dissolve in the same glass of water. And yet, according to current scientific understanding, the two substances sitting in those dishes could not be more different at the level of their atoms. One is a mineral, ancient, simple, built from charged particles locked in geometric embrace. The other is a molecule, complex, organic, assembled by living systems over millions of years of biological refinement. And tonight we begin with these two small piles of white crystals and with everything they quietly contain. Salt and sugar are among the most studied crystalline substances in everyday chemistry. And yet, much of what they are happens at a scale far below anything the eye can register. The grains on that counter are not the interesting part. The interesting part is what is inside each grain and what happens when the grain stops being a grain at all. To begin at the most immediate level, the level of what can actually be seen, both salt and sugar appear white under ordinary light. This shared appearance is not coincidental, but neither does it reflect a shared structure. The whiteness of crystalline salt, known chemically as sodium chloride, arises from a specific optical behavior. When light strikes the surface of a sodium chloride crystal, it encounters a lattice of repeating planes arranged with near-perfect regularity. Each plane reflects a portion of the incoming light. Because the planes are oriented in multiple directions, light scatters outward simultaneously. No single wavelength is absorbed preferentially. The result is diffuse reflection across the full visible spectrum, the same scattering quality that makes fresh chalk appear white rather than bright, a softness without glint, and the eye reads it as white. Sugar, sucrose in chemical terms, produces its whiteness through a related but not identical mechanism. The sucrose crystal is less geometrically regular than salt at the macroscopic scale. Its internal arrangement is more complex, and its crystal faces meet at angles that differ from those of the cubic salt grain. When light encounters refined white sugar, it scatters across those irregular faces in a slightly more chaotic pattern. The grain still appears white, but with a quality that experienced observers sometimes describe as slightly more diffuse or slightly less sharp than the glint of salt.
Under a jeweler's loupe or even a simple magnifying glass, this difference becomes visible. Salt grains present flat, even surfaces, the geometry of a cube repeated endlessly, smaller and smaller, down to the atomic arrangement beneath. Sugar grains present a more fractured profile, edges that catch light unevenly, like very small pieces of a glass that was never perfectly flat to begin with. The contrast in crystal shape traces directly to their underlying chemistry. Sodium chloride crystallizes in what mineralogy classifies as the cubic system, the most symmetric of the 7 recognized crystal classes. The cube is not imposed from outside, it grows from within. Each unit cell, the repeating structural rodule, carries equal dimensions on all 3 axes, right angles at every corner, an arrangement of near total geometric regularity. The result, as crystal faces develop, is a tendency toward flat, square surfaces and right-angled edges. A grain of ordinary table salt, examined carefully, will often show this cubic tendency even at the millimeter scale. Slightly flattened planes, corners that approach 90 degrees, an overall geometry that reflects the tight, regular packing of sodium and chloride ions inside. Sucrose, by contrast, crystallizes in the monoclinic system, a less symmetric class, its internal geometry tilted slightly off true, the way a book placed at a fractional angle departs from the clean edge of a flat shelf. That tilt propagates outward as the crystal grows, producing faces that are less uniform, edges that are less even, and an overall grain shape that tends toward elongated, wedge-like or shard-like forms rather than cubes. Depending on the conditions under which it crystallized, the temperature of the solution, the rate of cooling, the presence or absence of trace impurities, a sugar crystal can look almost needle-thin or broadly flat, almost prismatic or almost blocky, but it will rarely look like a tube. There is a sensory note worth pausing on here. If a small amount of coarse sea salt and an equal amount of raw cane sugar were placed separately on a smooth surface and examined, the difference in texture would be immediate, perceptible through the slightest pressure. Salt grains resist, then yield. They are harder than they appear, and their flat faces produce a faint, clean grinding sensation, like very fine stone. Sugar grains feel different, a slight roughness that is less sharp, slightly more yielding under pressure, with an almost granular softness just before the grain gives way. The density of salt is measurably higher. Sodium chloride registers at approximately 2.16 grams per cubic centimeter, while sucrose sits closer to 1.59. The difference is not dramatic by weight alone, but it is enough that a measured cup of table salt is noticeably heavier than the same volume of granulated sugar. The salt compacts differently. It fills space differently. Its grains, being denser and more uniformly shaped, tend to settle more tightly against each other. Moving deeper into what each grain actually contains, the distinction becomes fundamental. Sodium chloride is an ionic compound. It contains no molecules in the conventional sense. Instead, it is a continuous lattice of charged particles.
sodium ions carrying a positive charge and chloride ions carrying a negative charge, alternating in a three-dimensional checkerboard arrangement, so regular that it extends without interruption across the full interior of every grain. There is no boundary within the single crystal of salt between one unit and the next. The lattice simply continues, repeating in all three directions until the surface of the crystal is reached. A single grain of table salt at a typical size, perhaps half a millimeter across, contains, according to current estimates, on the order of 1 quintillion individual ions. That is a number with 18 zeros, all of them arranged, ion by ion, in the same alternating cubic pattern. Sucrose is something entirely different in structural terms. It is a molecule, a discrete bounded arrangement of atoms that has a specific size, a specific shape, and defined edges where the molecule ends and the surrounding space begins. The sucrose molecule is built from two simpler sugar units, glucose and fructose, joined together through a chemical linkage. Across those two rings, the molecule contains 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms. Each of these atoms occupies a defined position in three-dimensional space, bonded to its neighbors through shared electron pairs, a kind of bonding called covalent, more like a handshake than a lock, where atoms hold each other by sharing rather than by charge alone. When sucrose crystallizes from solution, the molecules stack against each other in the monoclinic arrangement described earlier, held in place not by the strong ionic attraction that locks salt's lattice together, but by a network of weaker interactions between neighboring molecules. The crystal is real, the structure is ordered, but it is a different kind of order. Molecules packed in a pattern rather than ions fused into a continuous lattice. What this means at the visible scale is that the two crystals, despite appearing similar on a kitchen counter, are built on different organizational principles entirely. One is a mineral. The other is an organic compound produced by biological chemistry. Salt forms wherever sodium and chloride ions come together in solution under appropriate conditions, in evaporating seawater, in ancient underground deposits, in laboratory glassware. Sugar, in the form of sucrose, is assembled exclusively by living plant cells, specifically in the cytoplasm of mesophyll cells in sugar-producing plants such as sugar cane and sugar beet, through the biochemical process of photosynthesis and subsequent enzymatic assembly. No purely geological or inorganic process, according to current scientific understanding, produces sucrose. This distinction, mineral versus organic product of living chemistry, is one of the deepest differences between the two substances, and it will run beneath every layer of this narration, the way a low, steady sound runs beneath a quiet room. The salt in the dish on that kitchen counter has no biological history. It has never been part of a cell, a tissue, or a metabolic pathway. The sugar in the adjacent dish has never existed anywhere except inside or in immediate proximity to a living system. Every grain of sucrose, wherever it was grown, carries in its molecular architecture the record of photosynthesis, of carbon drawn from the air, of water drawn from the soil, of solar energy captured and converted into the chemical bonds that hold those 12 carbon atoms and their companions in their precise arrangement. Neither of these facts is a source of drama. They are simply the structural realities of two substances that human chemistry has been refining and using for thousands of years, and that molecular science has been mapping in increasingly precise detail for just over a century. Both salt and sugar can rest in a dish on a counter under a dim light. Both will stay exactly as they are, crystalline and quiet, until they are dissolved or heated or otherwise disturbed. And for now, nothing needs to be disturbed at all. I know you have probably been confused, too, when you see salt and sugar sitting next to each other. I once wanted to add salt to my salad and realized I had grabbed the sugar instead, because in most homes we keep them right next to each other, and sometimes the containers look almost identical. Even though they look so similar, they are completely different. Their taste, their chemistry, everything. The first layer of a comparison between two materials is almost always the surface, not the deep surface, not the crystallographic surface, but the surface as it presents itself to an attentive room. What the eye sees before any instrument is brought near, what the fingertip detects before analysis can describe it. This layer tends to be underestimated because it is immediate, because it arrives without effort, and because the two white substances on that shelf give every appearance of having nothing to distinguish them at this level. That appearance does not hold for long. Both refined table salt and granulated white sugar appear white under ordinary daylight and artificial light. Neither appears off-white, neither appears gray or yellow or faintly blue. Both register clearly as white, the particular optical signature that the eye associates with surfaces that reflect light broadly, without absorbing or favoring specific wavelengths. But neither substance contains any white pigment, neither has been treated to produce whiteness. The whiteness is not a property of the material in any chemical sense. It is a structural effect produced entirely by the geometry of the crystal surfaces as they are encountered by incoming light. I consider that most of us did not know about this fact, right? Because I didn't either. I never thought about this. During my whole life, I considered sugar and salt to be white. But together we are learning that it is. It is crystal surfaces and incoming light. The mechanism is the same one that makes fresh snow white, though snow is composed of colorless water, or seafoam white, though seawater and air are both transparent. When light strikes a crystal surface, a portion of it reflects. A single flat surface returns that light as a single reflection, clean, directional, potentially transparent if the crystal is large enough and the geometry is right. But a powder is not a single surface. It is millions of surfaces stacked and angled in every possible orientation within the space of a few cubic centimeters, each one catching a fraction of the incoming light and returning it in a different direction. The cumulative effect of those millions of misaligned reflections is that light comes back to the eye from every angle simultaneously, which the visual system reads as white. The more surfaces, the more complete the whiteness. A coarsely ground salt is sometimes slightly less opaque than a finely milled one, simply because fewer surface boundaries exist per unit of volume.
According to current optical understanding, the whiteness of the grain is the whiteness of accumulated surfaces, not the whiteness of the material itself.
This distinction becomes visible when either substance is allowed to form a single large crystal under slow and undisturbed conditions, a process that requires patience and the absence of any vibration or contamination. A single crystal of sodium chloride grown carefully from a saturated solution is not white. It is essentially clear, with flat faces and a glassy interior through which text can be read, or through which a candle flame appears only slightly distorted. The salt crystals sold in some mineral collections for display purposes often carry this quality, a cool transparency, slightly smoky at the edges, nothing like the white powder in a kitchen shaker. A single crystal of sucrose grown under the same conditions, suspended on a thread in a jar of saturated sugar solution over several days, is also transparent, pale and glassy, with a warmth to its clarity that is different in character from the mineral coolness of salt, but equally removed from the white opacity of granulated sugar. Both materials, at the scale of the single crystal, are effectively clear. The whiteness belongs to the crowd, not to the individual. As far as I know, salt comes in many forms: large grains, coarse flakes, fine powder, and most of the time I buy the tiny one that have very tiny grains. The visual quality of each grain also differs in ways that extend beyond the baseline white. Under a kitchen lamp or a strong directed light, a small quantity of salt held in the hand scatters light in a way that is often described as cold or pointed. Small, bright, cleanly defined flashes from the flat cubic faces, each one returning light in a sharp angle before it is gone. The impression is precise. Each reflection is brief and specific, arriving and departing without lingering. A similar quantity of sugar under the same light returns something different, a more diffuse shimmer, spread across more angles, less defined at any single point, with the light distributed rather than concentrated into discrete points. Salt's glitter has edges. Sugar's glitter is softer, more even, less directional. The difference is subtle, and it requires attention to catch, but it is consistent, and it is a direct expression of the different geometries that the crystal faces of each material present to the light. I know how difficult it is to tell them apart, which one is salt and which one is sugar, if you place them side by side. Maybe you can guess. Unless you taste them, you cannot be certain, right? But I also learned that when you observe how they reflect light, you can see how different they are. The weight of each substance is another property that presents itself without instruments, through the hand. A volume of salt and an equivalent volume of sugar are not the same weight. Salt, at approximately 2.16 grams per cubic centimeter, is measurably denser than sugar, which sits at approximately 1.59 grams per cubic centimeter, a difference of more than a third by volume. The reason involves two things acting together. The particles that make up salt, sodium, and chloride ions are packed into a highly efficient cubic arrangement that leaves comparatively little empty space between them, the way stacked cubes in a container waste less room than an equivalent pile of irregular objects.
The particles composing sucrose, by contrast, arrange themselves into a more oblique geometry that is ordered and stable, but leaves proportionately more empty space between molecules. At the same time, the individual atoms in salt are denser than the carbon, hydrogen, and oxygen atoms that compose sucrose. Both effects point the same direction. Salt is heavier for its volume. The difference is not dramatic. Holding a teaspoon of each is not like comparing stone and feathers, but it is real, and it is there in the hand as a consistent, faint quality of compactness in salt that sugar does not carry. When either substance is touched, both are cool against the skin. All dense crystalline solids at room temperature read as somewhat cool against the warmth of a fingertip, because they conduct heat away from the skin's surface faster than air does. The same principle that makes a marble countertop feel cold even when the room is warm, or that makes a ceramic tile underfoot feel cooler than a wooden floor at identical temperatures. Salt, however, carries a quality often described as exceeding what its measured temperature would suggest, a specifically mineral coolness, something in the density and ionic character of its structure that draws warmth from the skin with a slightly greater efficiency than the grain temperature alone would predict. Sugar, with its lower density and the more complex geometry of its surface, delivers a marginally less pronounced version of the same effect under identical conditions. Both read as cool. Salt reads as slightly cooler. The difference is not enough to announce itself. It is the kind of thing that becomes apparent only when both are handled in deliberate sequence, one immediately after the other. Maybe you have touched both of the sugar and salt thousands of times in your whole lifetime, but probably you have not felt the difference in how cold they feel. It goes completely unnoticed. It is just wonderful. Both are dry in their crystalline state, genuinely, completely dry in the way that stable inorganic and organic crystals are dry, holding no surface moisture under ordinary humidity conditions when stored appropriately. Neither is sticky in this state. A dry grain of sucrose has none of the adhesiveness that dissolved or partially dissolved sugar is known for. It does not cling to skin or to adjacent grains. It rests and stays resting without any tendency to bind. Salt, in the same condition, is equally inert to the touch. A small pile can be moved across a dry surface without leaving any residue, without bonding, without drawing attention to itself through any behavior beyond its weight and its geometry. The behavior changes when moisture is introduced. If a slightly damp fingertip contacts the surface of a sugar grain, the outermost layer of the crystal begins to dissolve almost immediately, and dissolved sucrose in even small concentrations has a strong adhesive quality, the way a spilled drop of honey or fruit juice leaves a surface tacky long after the bulk of it has been wiped away. The mechanism behind this adhesiveness involves sucrose's particular affinity for water and the network of interactions its molecules form in solution. But the effect is perceptible long before any explanation is needed. The surface becomes sticky the moment it is no longer entirely dry. Salt, under the same conditions of surface moisture, also begins to dissolve at the outermost layer, but dissolved sodium chloride, salt water, carries no comparable adhesive quality. It is wet, not sticky. The surface left by a dissolved salt grain is damp,
not tacky. A finger drawn through a thin film of dissolved salt and then drawn through a thin film of dissolved sugar registers the two states as clearly different, one simply wet, one carrying that faint particular resistance of dissolved sugar against the skin. The dissolved molecules of each substance behave in fundamentally different ways once they are in solution, and that difference can be registered by a single fingertip that has encountered both. I know how it feels when sugar is wet. One day, I no longer remember exactly how, my eyelids got sticky after I ate sugary things. Even after I washed my whole face, my eyelids still felt sticky for a while.
What texture the grain carries, before any chemistry, before any dissolution, purely in its dry, crystalline state, pressed between the pads of the fingers, is also distinct between the two. Salt grains, particularly in forms that have been cut or fractured rather than slowly grown, carry a geometry that the fingertip reads as flat-faced and slightly defined. Small edges that present themselves with a quiet regularity, the way a pile of tiny rectangular tiles would feel if moved through slowly, each one flat on its face and meeting its neighbor at a right angle. Sugar grains, fractured differently and angled differently by their internal structure, present a less regular surface to the fingertip, not sharper necessarily, but less uniform, with a quality that is sometimes described as finely uneven, as though the surface geometry of each grain is slightly less predictable than its neighbor. The difference is minor. It is not enough to announce itself in ordinary handling, but when attention is brought directly to it, it is consistently there. A quiet disagreement between two white powders that look, from any reasonable distance, like the same thing.
These are the surface properties, what the eye sees, what the hand weighs, what the fingertip registers, before anything is dissolved or heated or examined at a scale smaller than the grain. The two substances have already, at this level, shown themselves to differ in their weight, their whiteness, their light behavior, their coolness, and their response to moisture. Moving deeper into the structure, into the level where the geometry of each grain's surface begins to reveal how each one was built, where the arrangement of particles inside each crystal determines how it breaks and the sound it makes when it does, brings a different kind of detail into view. The further inward the examination goes, the more the two substances begin to inhabit entirely separate worlds. The surface differences noted in the previous layer, the texture, the weight, the optical behavior, are only the outermost expression of what is happening at a scale that no light microscope can fully resolve. To understand how salt and sugar are truly built, it becomes necessary to move past the grain itself and into the repeating geometry that determines everything the grain is capable of doing. This is the level of the crystal lattice, not a metaphor, but a precise architectural description of how matter organizes itself when the conditions are right. Crystal growth, in both cases, begins with a solution. Dissolve sodium chloride in water and then allow the water to evaporate slowly, or cool the solution below a critical temperature, and the ions that were freely moving through the liquid begin to encounter each other with increasing frequency. At a certain point of concentration, a sodium ion and a chloride ion come close enough that the electrostatic attraction between their opposite charges holds them together
instead of allowing them to drift apart again. Once that nucleus exists, additional ions from the surrounding solution are drawn to it. Think of two puzzle pieces finding each other in a dark drawer. The fit, once made, is not easily undone. Each ion settles into the position in the growing lattice that minimizes the energy of the overall arrangement. The sodium ions settle into positions surrounded by 6 chloride neighbors. The chloride ions settle into positions surrounded by 6 sodium neighbors. This arrangement, known as the rock salt structure, a kind of perfect, endlessly repeated stacking, like identical crates packed into a warehouse with no wasted space, is one of the most stable ionic arrangements known to material science. It repeats outward from the nucleus in all 3 dimensions simultaneously, building the crystal face by face, row by row, until the supply of ions in solution is exhausted or external conditions change. The geometry of this growth is directly responsible for the cubic shape of the final grain. Each face of the growing sodium chloride crystal corresponds to a specific crystallographic plane, a surface along which the repeating pattern of the lattice is exposed, like a cross-section cut cleanly through stacked oranges arranged in a crate. The dominant faces that develop under typical growth conditions are the ones parallel to the 3 pairs of opposite cube faces, and these are the faces that grow most slowly, accumulating new ions at the most measured pace. This measured pace of growth, sustained equally across all 6 equivalent faces, is what produces the near-cubic symmetry of the final grain. If growth conditions are altered, if certain impurities are present in the solution, or if temperature fluctuates, or if the solution is stirred, the relative growth rates of different faces can change, and the resulting crystal will deviate from the cube. Hopper crystals of salt, which form under certain rapid evaporation conditions, are a well-documented example. They develop the square outline of a cube, but with hollow, stepped faces, as though someone excavated each face inward from the edges, leaving only the frame. The ionic structure inside is identical to ordinary salt, but the habit of the crystal, the shape it adopts on the outside, reflects the dynamics of how ions arrived at the surface during growth. When I searched for the images of Hopper crystals, first I thought that someone had made them by hand. That was my first impression. The growth of a sucrose crystal from solution follows a different logic at almost every stage. The sucrose molecule, being far larger and geometrically more complex than a simple ion, must orient itself correctly before it can be incorporated into the growing crystal face. This requirement for molecular orientation, picture sorting oversized irregular keys onto a wall of hooks, each one needing to be rotated just so before it can hang, slows the rate of sucrose crystal growth compared to salt, and introduces a greater sensitivity to solution conditions. If the solution cools too quickly, or if seed crystals are not introduced at the right moment, sucrose tends to form a disordered, glassy solid rather than a true crystal, what is known as amorphous sugar, the structural state of hard candy and toffee. In confectionery, when crystallization does proceed, but without adequate control, the result is a different problem. A texture called graining, in which fine microcrystals form throughout a candy mass in an uncontrolled, uneven way. The difference between crystalline sucrose and amorphous sucrose is not a chemical difference. The molecules are identical, but a structural one. In crystalline sucrose, every molecule occupies a defined position in the monoclinic lattice. In amorphous sucrose, the molecules are frozen in a disordered arrangement, more like a very viscous liquid that has been prevented from crystallizing than like a true solid with internal geometric order. In my whole lifetime, I loved sweets so much. And it turns out the sugar inside hard candy is not a true crystal at all. And that detail was unexpected for me. The monoclinic unit cell of sucrose, the smallest repeating unit of its crystal structure, like a single tile that copied exactly and extended in every direction, produces the entire floor, contains 2 sucrose molecules. This is a meaningful contrast with sodium chloride, whose unit cell contains 4 sodium ions and 4 chloride ions, each of which is considerably simpler than a full sucrose molecule. The sucrose unit cell has 3 axes of different lengths, approximately 10.86 angstroms, 8.70 angstroms, and 7.76 angstroms, with one oblique angle of approximately 102.9 degrees between 2 of the axes. An angstrom is 1/10,000,000th of a meter, a unit of measurement that belongs to the world of atoms. The fact that the unit cell dimensions of sucrose can be stated with this precision reflects decades of X-ray crystallography research, in which beams of X-rays were directed at sucrose crystals and the resulting diffraction patterns analyzed to reconstruct the 3-dimensional arrangement of every atom in the structure. The 45 atoms in each sucrose molecule within the unit cell have been mapped to a resolution of fractions of an angstrom.
In the sodium chloride lattice, each ion is surrounded by neighbors at approximately 2.81 angstroms. The distance between the center of a sodium ion and the center of an adjacent chloride ion. This distance, called the ionic bond length, is the equilibrium position where attractive force between opposite charges is balanced by the repulsive force that arises when electron clouds begin to overlap, like 2 magnets held just far enough apart that neither pushing nor pulling wins. The spacing is consistent throughout the crystal, because the ions are identical in each of their respective types, and the lattice is perfectly regular. There is no variation in bond length from one sodium chloride pair to the next within a pure crystal. This uniformity is part of what makes the sodium chloride lattice so amenable to precise physical analysis. It is, in the language of crystallography, a highly symmetric structure with a small, simple unit cell. There is a sensory dimension to crystal growth that the numbers alone do not carry. The formation of a large salt crystal in an evaporating dish, carried out slowly over days or weeks, is a process of accumulation so gradual that it is invisible in real time. What begins as a clear solution becomes, by increments so small they cannot be distinguished moment to moment, a solid. The surface of the growing crystal does not look active. Under a microscope, though, the surface is covered in what are called growth spirals. shallow ramps, one ion layer high, that wind outward from structural imperfections in the crystal face and allow new ions to add themselves to the edge of each step, rather than having to nucleate on a flat surface. These spirals are not visible to the naked eye. They are features of the atomic scale. According to current crystallographic models, they represent one of the primary mechanisms by which grains of table salt are built, ion by ion, in sequence, over whatever duration the original crystallization took. Run a finger across a salt crystal's surface and feel almost nothing, a faint roughness, a cool edge, while knowing that beneath that apparent stillness, every flat plane was assembled step by step, ramp by ramp, at a scale that makes the finest grit feel smooth by comparison. Moving deeper into the internal architecture of the sucrose crystal, the network of forces that holds the molecules in their monoclinic positions is more varied than the simple ionic attraction holding salt together. Within a sucrose crystal, the molecules are bound to each other primarily through hydrogen bonds, interactions that form between the hydrogen atoms attached to oxygen in one molecule and the oxygen atoms of neighboring molecules, like the repeated gentle clasp of hands passed down a long table, each grip soft on its own, but the table held firm by the many of them together. Each sucrose molecule carries multiple hydroxyl groups, oxygen-hydrogen units, arranged around the periphery of its two sugar rings. These hydroxyl groups act as both donors and acceptors of hydrogen bonds, linking each molecule to several of its neighbors in a three-dimensional network. The hydrogen bond is weak individually, far weaker than the ionic bond in salt or the covalent bonds within the sucrose molecule itself. But there are many of them, distributed throughout the lattice, and their collective effect is sufficient to hold the crystal intact at room temperature and to give sucrose its characteristic melting behavior, which will be addressed in full in the chapter that follows. Actually, before I said that, it is too hard to recognize which one is sugar and which one is salt when we put them together. It is too interesting that we have been touched both of them thousands of times, but we did not think about them much. The hydrogen network in a sucrose crystal also explains something observable at the macroscopic scale, the way sugar behaves when it absorbs moisture. When water molecules from humid air reach the surface of a sucrose crystal, they are well equipped to disrupt the hydrogen bonds between sucrose molecules. Water molecules themselves are capable of forming hydrogen bonds, and they compete effectively for the bonding sites on sucrose's hydroxyl groups. The result is that a small amount of water at the surface is enough to begin dissolving the outermost layer of the crystal, releasing sucrose molecules into solution and blurring the geometric precision of the crystal face. Salt, held by ionic bonds that water disrupts through a different mechanism, solvation, in which water molecules surround and carry individual ions away from the surface, the way a crowd absorbs a single person and moves them from the door, behaves similarly at the surface, but the fundamental interaction is different. The hardness of a crystal, its resistance to scratching, is, at the atomic scale, a reflection of how difficult it is to displace one layer of the lattice relative to the next. In sodium chloride, this displacement brings ions of the same charge into proximity, and the resulting repulsion causes the crystal to cleave rather than deform, The crystal does not bend, it breaks cleanly. In sucrose, the situation is more complex because the lattice is held together by a network of weak directional hydrogen bonds rather than the non-directional electrostatic attraction of an ionic lattice. Sucrose crystals, when subjected to mechanical stress, tend to fracture along paths that break the fewest hydrogen bonds, which is to say, along planes where the molecular packing is least dense and the intermolecular contacts are fewest. The result is a fracture pattern that is less predictable than the cleavage of salt and produces edges that are sharper and more irregular.
There is a quality to the interior of each crystal that becomes apparent only when thinking about it at this scale, the scale of angstroms and unit cells and hydrogen bonds. Salt's interior is, in a certain measurable sense, simpler. Two types of particles, one type of bond, one type of arrangement, repeating without variation from surface to surface. It is a structure that can be described completely with very few numbers. Sucrose's interior is more complex, a large asymmetric molecule, a low symmetry unit cell, a network of hydrogen bonds of varying strength and geometry, an optical activity that reflects the asymmetry all the way down to the arrangement of atoms within a single molecular ring. Both crystals rest in the dish. Both appear equally still. The difference between the kind of stillness each represents is the difference between a wall of identical bricks laid in a single repeating pattern and a wall built from interlocking pieces of irregular stone, held together just as firmly, occupying the same apparent space, but assembled according to a far more elaborate internal logic. Heat is one of the most revealing forces that can be applied to a crystalline solid, not because it destroys, though at sufficient intensity it does, but because the way a material responds to rising temperature reveals, in measurable and observable terms, exactly what is holding it together. Salt and sugar, placed side by side on a kitchen counter, appear equally indifferent to the temperature of the room. Both stay unchanged through a warm afternoon and a winter night, without visible alteration. But raise the temperature slowly and deliberately, and the two substances begin to move in entirely different directions, directions that are precise in chemical terms and visible to anyone watching. Sodium chloride melts at approximately 801 degrees Celsius. This is a high melting point, considerably higher than most materials encountered in ordinary daily life, and a direct reflection of the strength of the forces holding the lattice together. Think of those forces as an enormous network of tiny magnets, every one locked to its neighbors across the whole crystal, each connection pulling with quiet but considerable strength.
To melt the crystal, to convert it from a solid with a fixed structure to a liquid where the pieces move freely, enough thermal energy must be supplied to overcome all of those connections simultaneously across the entire three-dimensional arrangement at once. The result is a melting point that places sodium chloride firmly in the category of high-temperature materials when compared to most organic and inorganic compounds encountered in everyday settings. At 800 degrees, the surrounding environment would glow with visible heat. The salt itself becomes a clear, moving liquid, a flow of freely drifting sodium and chloride pieces, still carrying their charges, still drawn to each other, but no longer locked in place. Sucrose begins to respond to heat at a far lower temperature, and its response, unlike salts, is not a simple transition from solid to liquid. When sucrose is heated, the first notable change occurs at around 160 degrees Celsius, where the crystal begins to melt. But this melting is not clean. It is the beginning of a chemical coming apart that proceeds simultaneously with the physical change. As the temperature rises through approximately 160 to 186 degrees Celsius, the sucrose molecules do not simply escape the crystal and begin moving as intact molecules in a liquid state. Instead, the heat is sufficient not only to free them from the crystal arrangement, but also to begin breaking the bonds inside each molecule itself. The connection joining the glucose and fructose halves, like a latch holding two small hinged boxes together, begins to crack under the thermal pressure. The sucrose molecule starts to decompose. This decomposition in its early stages produces a series of intermediate compounds. Water is released as parts of the molecular framework separate and recombine. The remaining carbon-rich structures begin linking together into longer, more complex arrangements, like a string of beads whose original sequence has been lost and which now form entirely new patterns of their own. These larger molecules absorb light differently than sucrose does, and the result is visible and progressive. The clear melt begins to take on color. This decomposition in its early stages produces a series of intermediate compounds. Water is released as parts of the molecular framework separate and recombine. The remaining carbon-rich structures begin linking together into longer, more complex arrangements, like a string of beads whose original sequence has been lost and which now form entirely new patterns of their own. These larger molecules absorb light differently than sucrose does, and the result is visible and progressive. The clear melt begins to take color. The first stage produces a pale golden liquid, warm and translucent. As the temperature rises further, the color deepens through amber, then brown, producing the range of compounds collectively known as caramel. The caramelization process is not a single reaction. It is a cascade of parallel and sequential chemical changes involving hundreds of distinct intermediate molecular species, most of which have not been fully characterized. Some of these intermediates are volatile compounds that rise from the surface of the hot liquid, the heavy, warm sweetness that fills a kitchen when sugar is held over prolonged heat. That smell is not a property of sucrose itself. It is a property of what sucrose becomes when the heat exceeds its tolerance of its internal bonds. The transformation of sugar under heat, the darkening, the aroma, the shift from crystalline white to amber liquid is one of the most familiar thermal transformations in cooking. The specific shapes of the volatile molecules produced during decomposition happen to fit particular receptor proteins in the nose with enough precision to produce a recognizable response, which is why the smell of caramelizing sugar reaches across a room and is recognized immediately without any knowledge of the chemistry behind it. Salt, by contrast, produces none of this complexity when heated to its melting point. Sodium chloride does not decompose when melted. Its pieces separate from their lattice positions and become mobile, but they remain exactly what they were: sodium pieces and chloride pieces. No new compounds form. No color change occurs. The molten salt is colorless, like the crystal it came from. No aroma is produced. The transition from solid to liquid is chemically a reversible one. Allow the melt to cool, and the pieces reorganize back into their cubic arrangement, producing a solid crystal essentially identical to the one that existed before. Melting sodium chloride is a physical change. Heating sucrose until it liquefies is simultaneously a physical and a chemical change, and once the chemical changes begin, they cannot be reversed by simple cooling. This difference in thermal behavior reflects the difference in bond types. The forces holding salt's lattice together, like a city of tiny magnets arranged in perfect squares, each clamped to the next, are strong, but they are bonds between separate pieces rather than bonds within a piece. Disrupting them releases the pieces from their fixed positions, but does not change the pieces themselves. The sodium piece that was part of a salt crystal is the same sodium piece in the melt, and it will be the same sodium piece when the crystal reforms on cooling. The internal bonds of sucrose, by contrast, the connections that hold the atoms within each molecule together, like stitches in a fabric, begin to break at temperatures well below what is needed to melt salt. And once they break, the atoms recombine into different arrangements. The molecule that existed before heating does not exist afterward. The thermal conductivity of a material, its ability to transfer heat from one point to another, is another property that separates salt and sugar in measurable terms. Sodium chloride has a thermal conductivity of approximately 6.5 watts per meter Kelvin. This is relatively high for a non-metallic solid. When one face of a salt crystal is warmed, the pieces near that warm face begin to vibrate more quickly, and they pass that increased vibration to their immediate neighbors, which pass it onward in turn, like a slow, organized relay running the length of the crystal. The regularity of the arrangement makes this propagation efficient. The warmth moves through cleanly, the way a hand placed on a cool stone surface on a warm evening can feel the day's stored heat releasing slowly outward through the material. Sucrose has a much lower thermal conductivity, approximately 0.126 watts per meter Kelvin in crystalline form. This value is roughly 50 times smaller than that of sodium chloride. The difference arises from the more complex structure of the sucrose crystal, large, irregular molecules packed in a less symmetric arrangement that scatter and absorb the flow of thermal vibration rather than passing it cleanly through. The vibrational energy introduced at one surface of a sucrose crystal is dispersed and absorbed by the molecular complexity of the interior. A piece of salt crystal brought to a warm surface would reach the temperature of that surface more quickly than a piece of sucrose crystal of the same size under the same conditions. Moving to lower temperatures, both substances are stable across the full range encountered in ordinary storage conditions, from freezing to room temperature and beyond. Neither sodium chloride nor sucrose undergoes a structural change within this range,
but the behavior of each in the presence of water near freezing is different in a practically notable way. Sodium chloride dissolved in water lowers the freezing point of that water, a property called freezing point depression, and it does so more effectively than most dissolved substances because each unit of salt that dissolves splits into two separate particles in the water, one sodium piece and one chloride piece. Each particle contributes independently to the effect, like two separate voices lowering the temperature of the water rather than one. According to current scientific data, a 1 molal solution of sodium chloride depresses the freezing point by approximately 3.4 to 3.7 degrees Celsius, a range that reflects the real behavior of the solution under measurement. Sucrose, dissolving as intact molecules rather than splitting apart, produces only one particle per unit and lowers the freezing point by a smaller amount. A 1 molal sucrose solution depresses the freezing point by approximately 1.86 degrees Celsius. The salt solution, at equal concentration, has roughly twice the freezing point effect of the sucrose solution, a direct result of that splitting into separate particles upon dissolving. The specific heat capacity of a substance, the amount of energy required to raise the temperature of 1 gram of it by 1 degree Celsius, is another thermal property that separates the two crystals. Sodium chloride has a specific heat capacity of approximately 0.87 joules per gram per degree Celsius. Sucrose has a higher heat, approximately 1.24 joules per gram per degree Celsius. This means that sucrose requires more energy input to raise its temperature by the same amount, like a thicker wall that takes longer to warm all the way through. The difference traces again to the molecular complexity of sucrose, a larger structure with more internal connections, capable of absorbing thermal energy through a wider range of internal movements, like a larger instrument with more strings to receive the vibration, rather than only through the simpler lattice vibrations characteristic of the ionic solid. There is a stillness to all of this, considered at the level of a room temperature crystal sitting undisturbed on a shelf. At room temperature, every piece in the salt lattice is vibrating, oscillating around its resting position with an amplitude that reflects the thermal energy of the environment. The crystal feels cool and faintly hard to the touch, with a smooth mineral surface that gives no indication of the constant internal motion that careful measurement can confirm. The vibrations are far too small to observe directly, even with sensitive instruments, but they are real and they are continuous, a kind of ordered trembling that never stops as long as temperature remains above absolute zero. Sucrose crystals at the same temperature are also in motion at the atomic scale, every internal angle flexing slightly, every atom displaced from its average position by the same thermal energy, the large molecule moving not rigidly, but with a collective flexibility that comes from having so many internal connections to distribute the motion across. Salt and sugar appear still, but the atoms inside them, much like a human heart pumping blood, do not stay in place, they tremble. Now you may ask, where can we see this, or how can we even know? Without specialized scientific equipment, of course, it is impossible for us to see or feel this. The thermal behavior examined in the previous chapter was a kind of surface conversation, a measurement of consequences rather than causes. The melting points, the decomposition temperatures, all of these are readable effects of something operating at a level that heat alone cannot reveal. To understand why salt and sugar respond to temperature the way they do, it becomes necessary to travel one level further inward, not to the crystal, not to the molecule, but to the bond itself, to the nature of the force that holds atoms in place, and to the precise conditions under which they let go. Think of a bond as a kind of agreement between atoms. In some agreements, one particle gives something and the other receives it. In others, both hold the same thing between them, sharing the arrangement. Salt and sugar represent both types. The difference between them at this scale accounts for nearly everything that follows. The ionic bond that holds sodium chloride together begins with a single electron, a loosely orbiting particle that sodium carries alone in its outermost shell. A neutral sodium atom has 11 protons in its nucleus and 11 electrons arranged around it in layered regions. 2 occupy the innermost shell, 8 fill the second, and 1 sits alone in the third, farther from the nucleus than the rest, partially shielded by the 10 electrons beneath it, held with less force than any of the others. It is like a key left on the outermost hook of a long row, the one most easily reached, the one most likely to be taken first. The energy required to remove that single outer electron from a neutral sodium atom, its first ionization energy, is approximately 4,962 kilojoules per mole. On its own, that number is difficult to place. What gives it meaning is the comparison. Removing a second electron from the now complete inner shell of the resulting ion requires approximately 4,562 kilojoules per mole, nearly 10 times more. The gap between those two values is sharp enough to function as a boundary. It is the reason sodium, under ordinary chemical conditions, always loses exactly 1 electron and stops. The resulting sodium ion, with 11 protons and 10 electrons, carries a net positive charge of 1 unit, settled, stable, no longer in pursuit of anything. Chlorine approaches the arrangement from the opposite side. A neutral chlorine atom carries 17 protons and 17 electrons, 2 in the innermost shell, 8 in the second, and 7 in the outermost, 1 position empty out of 8. The tendency to fill that vacancy is measurable as a release of energy. When a neutral chlorine atom gains 1 electron, it releases approximately 349 kilojoules per mole, a value among the highest of any element. The chloride ion that results, carrying 18 electrons and 17 protons, settles into a complete outer shell, quiet, full. When a sodium atom and a chlorine atom meet under appropriate conditions, the transfer of that single outer electron from one to the other is favorable for both. Each particle ends the exchange with a completed outer shell. Each carries a charge that draws it toward the other. The bond that forms is not a sharing arrangement. No electrons are held jointly between them. The sodium ion and the chloride ion remain as separate, distinct particles, each stable on its own, held at their equilibrium distance by the balance between attraction and the resistance of their electron clouds. Two arrangements that have found their resting position, like two small weights that have settled to either end of a balanced scale, neither pulling toward the center, neither drifting away.
In the salt crystal, this pairing repeats across every dimension. Each sodium ion is surrounded by 6 chloride neighbors. Each chloride ion is surrounded by 6 sodium neighbors. The pattern extends outward through millions of paired charges, every ion held in place by the combined pull of everything around it. The collective strength of this arrangement, according to current models of ionic bonding, functions as the lattice energy, measured at approximately 787 kilojoules per mole for sodium chloride. That is the energy required to pull 1 mole of the crystal completely apart into isolated ions in a vacuum. It is not the strength of a single bond. It is the accumulated weight of an entire interlocking system, every charge holding every other in a continuous 3-dimensional grid. The mechanical character of that grid is specific. It does not soften under pressure. Apply force to a salt crystal at the wrong angle, and it holds, then snaps cleanly along the geometric planes where rows of ions meet. The sound of it is short and definitive. No gradual yielding, no slow accommodation. The structure is rigid in the way a precisely arranged set of small permanent magnets set into a square grid is rigid. The geometry holds until the applied force exceeds it, and then the whole arrangement separates at once, leaving 2 clean faces where the break occurred, each one as orderly as the original surface.
Within a sucrose molecule, the arrangement is different in kind. Atoms here do not transfer electrons, they share them. A covalent bond places a pair of electrons in the space between 2 bonded atoms, drawn to both nuclei at once. The carbon-carbon, carbon-oxygen, and oxygen-hydrogen bonds within sucrose are all built this way. Within a single molecule, 45 atoms are connected by a continuous network of these shared electron bonds, each held at a specific angle determined by the geometry of the electron pairs involved, each one slightly flexible, capable of bending a few degrees under mechanical stress, absorbing and redistributing force in a way the ionic lattice cannot. The molecule has a give to it that salt does not. Not softness exactly, but a capacity to adjust rather than simply hold or break. The individual bonds have measurable strengths. The carbon-oxygen bond in sucrose holds at approximately 360 kilojoules per mole. The carbon-hydrogen bond, somewhat stronger, holds at approximately 413 kilojoules per mole. The oxygen-hydrogen bond of the hydroxyl group sits at approximately 459 kilojoules per mole, the strongest of the 3. These are the bonds that begin to give way when sucrose approaches its decomposition temperature. They break in sequence, not all at once, beginning with the most accessible, the process releasing the conditions for the next stage, color deepening and smell emerging gradually as different regions of the molecule give way. This is why the heating of sucrose is a progression rather than a single event. The ionic lattice of salt requires, based on available evidence, a collective threshold to be crossed. The structure holds until it does not. Sucrose breaks one bond at a time, each one telling a different part of the same slow story. Moving deeper into how these molecules relate to their neighbors, sucrose carries a quality that the ionic structure of salt does not. Oxygen appears throughout the sucrose molecule in each of its hydroxyl groups and within its ring structures. Oxygen has a strong tendency to draw the shared electrons in any bond toward itself, to pull them slightly away from the adjacent carbon or hydrogen and hold them closer. The result is a region of slight negative charge at each oxygen and a corresponding region of slight positive charge at each hydrogen bonded to it. The shift is small. The charge is partial, not complete, a lean rather than a transfer. But sucrose carries 8 of these hydroxyl groups, each one generating this asymmetry, each one extending a kind of quiet attraction toward the complementary partial charge on a neighboring molecule. In a crystal where every molecule participates in this network, the total effect becomes a meaningful, cohesive force, more numerous than ionic attraction, more directional in geometry, quieter in character. The partial charges within that network are too small to experience at any ordinary scale. But in a crystal of sucrose, there are on the order of 10 to the 21st such interactions occurring across the structure simultaneously, a number whose magnitude is easier to appreciate through its consequences than through the count itself. Salt's ions carry full charges, not partial ones. There is no preferred direction to the attraction. Sodium is equally drawn to all 6 of its chloride neighbors, and the lattice behaves identically in any equivalent direction. The sucrose crystal, by contrast, has different properties depending on the axis along which it is measured, because the hydrogen bond network introduces an asymmetry that the ionic lattice does not possess. When each substance meets water, the difference in charge character produces a difference detectable with a simple electrical test. Salt releases ions into solution. The water molecules orient themselves around each ion, negative ends toward sodium, positive ends toward chloride, drawing each one away from the crystal surface and into the liquid. The resulting solution contains freely mobile charged particles. Under an applied electrical potential, they migrate, sodium toward the negative electrode, chloride toward the positive, and the solution conducts electricity. The concentration of dissolved salt can be estimated from the conductivity alone. When salt is mixed with water, the water begins to cool, but when sugar is mixed with water, the water begins to warm. It is nearly impossible for us to feel this by touch because the temperature of the water changes only slightly. We can only detect it with specialized equipment. And the most interesting part is this: electricity passes through salt water, but it does not pass through sugar water. The reason can be explained like this. In salt water, the salt itself breaks into 2 separate parts, and as a result, salt water conducts electricity. Sugar water, on the other hand, is the opposite.
When sugar is mixed with water, the sugar remains completely intact and no separation occurs. Because of this, electricity does not pass through it. The stability of salt under ordinary ambient conditions follows directly from the nature of its ions. The sodium ion, having released its outer electron, now carries the electron configuration of neon, complete, stable, with no tendency to react further under normal conditions. The chloride ion mirrors the configuration of argon. Both arrived at their most stable states when the original electron transfer occurred. There is nothing the surrounding environment can offer them that would improve on what they already have. Salt, left undisturbed, remains salt. Sucrose carries its bonds with less finality. The molecule is stable under ordinary dry conditions, but specific sites within its covalent structure, particularly the glycosidic bond between its glucose and fructose units, and the carbonyl groups latent within its ring arrangements, are accessible to heat, to acid, and to certain biological agents in ways that the ionic structure of salt is not. Salt has no internal architecture that a chemical agent can selectively target. Its ions are already in their most stable configurations, and nothing within the structure differs from the rest. Sucrose, by contrast, carries within its network of shared electrons specific positions of greater reactivity, points where the molecule's internal complexity becomes a kind of openness to the world. That difference will continue to shape everything that unfolds in the minutes ahead. I don't know if you think the same way as I do. When I think of salt, I always picture rocks, white, crystalline cliffs. It gives off a feeling of an icy, frozen place. When I taste salt, it feels like I've come back to myself. We naturally scrunch our faces when we taste salt, and in that exact moment, a feeling comes over me that I cannot put into words, like waking up from a dream and finding yourself again. Sugar, on the other hand, is the complete opposite. When I think of sugar, I picture a room with pink walls, magnificently decorated inside. And most of all, I picture all kinds of different, colorful sweets inside it. These are all my personal thoughts, of course, and it is perfectly normal if you see it differently. The bond chemistry examined in the previous layer becomes most consequential, not in the laboratory, but in the practical context of what these two substances do when they encounter living systems. Specifically, the microorganisms that share every surface, every solution, and every food environment with them. Salt and sugar have both been used for thousands of years as preservatives, and the mechanism by which each one achieves this effect is among the more elegant demonstrations of physical chemistry operating at a biological scale. The preservation action of both substances rests on a single principle: osmosis. Think of it the way water quietly seeps through a damp cloth toward the drier side, not because anything pushes it, but simply because it moves toward evenness. Water moves across semi-permeable membranes, membranes that allow water through but restrict the passage of dissolved particles, from regions of lower solute concentration to regions of higher solute concentration. This movement is not driven by any active biological process. It is a passive physical consequence of the tendency of systems to level out their differences. The membrane of a bacterial cell is in exactly this sense.
When a bacterium finds itself in an environment where the external concentration of dissolved particles is higher than the concentration inside the cell, water moves outward through the membrane, from the dilute interior toward the concentrated exterior. The cell loses water. Its internal pressure drops. Its biochemical processes, which depend on the precise concentration of internal molecules and ions, become disrupted. Under sufficient osmotic stress, the cell cannot maintain the functions necessary for survival or reproduction.
Salt achieves this effect with particular efficiency because of ionic dissociation, a process something like breaking a pear into two separate individuals, each one now exerting its own independent weight on the surrounding environment. 1 unit of dissolved sodium chloride produces 2 particles in solution, 1 sodium ion and 1 chloride ion, and both contribute independently to the osmotic pressure of the surrounding environment. A given mass of salt therefore generates a higher osmotic effect than the same mass of a substance that dissolves without dissociating. Sugar achieves osmotic preservation through the same mechanism, but because sucrose dissolves as intact molecules, 1 particle per formula unit, it requires a greater mass of dissolved substance to achieve the same osmotic pressure as a given mass of salt. In practice, sugar-based preservation typically uses very high concentrations. The sugar content of traditional jams and preserves is often above 60% by weight, whereas salt-based preservation can be effective at considerably lower concentrations by mass. The texture of what this means for a bacterial cell can be approached through an analogy. A cell under severe osmotic stress, surrounded by a highly concentrated solution of either salt or sugar, behaves something like a water-filled balloon placed in a very dry environment. The water inside the balloon moves toward the dry exterior through the material of the balloon wall. The balloon deflates, loses its shape, and its contents become concentrated. There is a quietness to how this unfolds. Nothing sudden, nothing forceful. For a living cell, this concentration of the interior disrupts the delicate balance of ions and molecules that biochemical reactions require. Enzymes lose their functional geometry. Membrane integrity can be compromised. The sequence of effects is not instantaneous, but it is, at sufficiently high external concentrations, irreversible. The selective effectiveness of salt and sugar against different classes of microorganisms is a subject of ongoing study in food microbiology. According to current scientific understanding, most common spoilage bacteria are inhibited at sodium chloride concentrations above approximately 10% by weight in water. The water activity of the solution drops below the threshold at which most bacteria can sustain growth. Certain salt-tolerant organisms, classified as halophiles, can survive and grow in near-saturated brine. Sugar preservation at high concentrations similarly inhibits most common bacteria, though yeasts and certain molds tend to tolerate high sugar environments better than bacteria do. This is why high sugar environments can still support fermentation, a fact exploited in various traditional food preparations.
moving deeper into how each substance interacts with the water in its environment. Water activity is a measure of the availability of free water molecules in a system, expressed on a scale from 0 to 1. Think of it as a measure of how many water molecules are still free to wander versus how many have been drawn into service around dissolved particles. Pure water has a water activity of exactly 1. As solutes are dissolved, water molecules become associated with the dissolved particles through solvation and hydrogen bonding, reducing the proportion of water molecules that are freely available to participate in biological or chemical processes. Sodium chloride, through the hydration shells that form around each ion, a close layered arrangement, the way fine dust clings to a damp surface, ties up water molecules with considerable efficiency. Sucrose, through the hydrogen bonds between its hydroxyl groups and surrounding water, also reduces water activity, though through a different mechanism and with different efficiency per gram of dissolved substance. There is a sensory dimension to concentrated solutions of each substance that is worth pausing on. When we add a lot of salt to water, that water becomes heavier than ordinary water. And when we pour that salt water onto glass, after it dries, we can see that it leaves behind a white crystalline mark. Let me give an example from ordinary life. Say you put on a black shirt and sweat heavily. For example, you put on a black t-shirt and ran on a treadmill for a long time and sweated as if someone had poured a bucket of water over you. After your workout, you will most likely take that black shirt off and throw it in the wash. But if you wait for your sweat to dry completely on that black shirt, you will see that there are white marks on that black shirt. Why, you ask? Yes, because our sweat also contains salt. And I have experienced this myself many times after heavy cardio workouts. At the same time, when we add a lot of sugar to water, the water takes on a form similar to syrup or honey. In other words, it thickens. If you also pour a drop of sugar water onto glass and wait for it to dry, you can observe that the drop leaves behind an invisible, transparent mark. The chemical stability of sodium chloride in the presence of common food environments, mild acidity, ambient oxygen, moderate temperature, is essentially complete. Salt does not react with dilute acids under ordinary conditions. It does not oxidize in air. It does not react with the organic molecules typically present in food environments. Its preservation action is purely physical, osmotic, without any chemical interaction with the organisms it inhibits. This chemical inertness is part of what makes salt such a reliable and long-studied preservative. Its effectiveness does not diminish through chemical change over time, and it does not introduce reactive byproducts into the preserved material. Sucrose, by contrast, is susceptible to a chemical reaction called hydrolysis under acidic conditions or in the presence of the enzyme invertase. Hydrolysis works the way a single drop of water quietly loosens a knot. One water molecule is inserted across the glycosidic bond connecting the glucose and fructose units of the sucrose molecule, cleaving it and producing one free glucose molecule and one free fructose molecule. The resulting mixture is called invert sugar.
A term reflects the fact that the optical rotation of the mixture, the direction in which it turns polarized light, is reversed relative to the original sucrose solution. Invert sugar is sweeter than sucrose on a gram basis because fructose alone is sweeter than sucrose, and the mixture of glucose and fructose is sweeter than the intact sucrose molecule. This hydrolysis occurs gradually in mildly acidic environments, such as fruit preserves, and more rapidly at elevated temperatures or lower pH values. The preservation chemistry of sucrose is therefore not entirely static. The molecule itself changes slowly over time in certain environments, in a way that sodium chloride does not. What both substances share in the context of preservation is the capacity to alter the physical environment of microorganisms in ways that are measurable, predictable, and consistent across a wide range of biological targets. The action is not directed at any specific component of a bacterial cell. It is not a chemical attack. It is a physical consequence of thermodynamics, the movement of water down its concentration gradient, following the same principle that governs water movement in any system where a membrane separates regions of different solute concentration. The sophistication of the preservation effect lies not in any special property of salt or sugar themselves, but in the fundamental behavior of water in the presence of dissolved matter. Both dishes on that counter, then, contain substances that interact with water in ways that have shaped food preparation across thousands of years of human history. One through the efficiency of ionic dissociation, one through the mass of its molecular solubility. Both effective, both physical, both operating according to the same underlying thermodynamic principle, expressed through chemistries that could not be more structurally different from each other. The facts at this level become geometric, not the geometry that can be seen with the eye, the measured angles of a crystal face or the flat planes of a split grain, but the geometry of space itself at a scale where individual atoms are the landmarks and electron clouds are the territory. At this depth, salt and sugar stop being different in taste or behavior alone. They become different in the way space has been organized around them. Two different answers to the same quiet question: how does matter arrange itself into stability? Moving deeper into the structure of salt, the sodium ion at the center of its lattice sits surrounded by exactly 6 chloride neighbors, positioned at the 6 corners of a geometric form called an octahedron, a solid with 8 triangular faces and 6 evenly spaced points extending outward, like the ends of 3 perpendicular rods intersecting at a single center. The symmetry of the cubic lattice ensures this arrangement without approximation. Each sodium ion is equidistant from all 6 of its neighbors. Each chloride ion rests at the center of its own matching arrangement. The pattern interlocks. Every such environment shares its edges and corners with the next, repeating without deviation across the full interior of every grain. There are no irregularities in this pattern, no points where the symmetry relaxes or gives way. According to current solid-state chemistry, this is among the more geometrically stable arrangements matter is known to take, reached through the internal logic of ionic sizes and charge distributions without outside instruction.
The electron cloud of the sodium ion reflects this symmetry directly. Stripped of its outer electron, the sodium ion carries a complete second shell of 8 electrons, arranged in a configuration of high internal order. Mapped by quantum mechanical calculation and confirmed by X-ray diffraction studies, the shape of the ion's electron density is approximately spherical, smooth and even in every direction, like a small settled bead resting undisturbed. The chloride ion, carrying 18 electrons in complete shells, presents the same quality, slightly larger, also approximately spherical. Between adjacent ions in the lattice, a small gap persists, a narrow separation maintained by the balance of electrostatic attraction and the outward pressure of their electron clouds. The electron clouds do not significantly overlap. The bond is the pull between two charged spheres, held at the precise distance where inward attraction and outward resistance come exactly into balance. The faint, cool weight of a salt grain pressed between two fingers, its density, its quiet resistance to compression, is the macroscopic surface of this equilibrium, replicated across every ion pair within the grain. Beneath that surface quality lies a very different arrangement in sucrose. The electrons within the sucrose molecule are not gathered into spherical shells around individual nuclei. They are shared across bonds, drawn into the spaces between atoms, concentrated along the paths connecting carbon to oxygen, carbon to carbon, oxygen to hydrogen. Each of these connections is a bonding orbital, a region of elevated electron density where two atoms have pooled their electrons into shared territory, the way two hands closed around the same object form a single continuous grip between them. The shape of the molecule, the angles of its rings, the directions of its bonds, emerges from the sum of all these shared arrangements. Unlike the ionic lattice, which is built from the repetition of two simple spherical units, the sucrose molecule has no center of symmetry. Every part of it is geometrically distinct from every other part. What becomes interesting at the molecular level is the behavior of the hydroxyl groups, the 8 sites in the sucrose molecule where an oxygen atom carries a hydrogen at its outermost point, like the tips of reaching branches. Each of these oxygen atoms holds 2 pairs of electrons not involved in bonding at all. These are the lone pairs, occupying regions of space directed away from the attached atoms, available to neighboring molecules. When a neighboring sucrose molecule's hydroxyl hydrogen comes within roughly 1 to 2 angstroms of one of these lone pairs, a distance shorter than the wavelength of visible light, shorter than almost anything that can be directly observed, an attraction forms between the partially positive hydrogen and the electron-dense lone pair. This is a hydrogen bond. It is quieter than the ionic bond, softer in its pull, but it is not weak, and it is directional. The bond is strongest when the donor oxygen, the hydrogen, and the accepting oxygen align in an approximately straight configuration, 3 points along a single axis, like 3 small weights hung on the same fine thread. The sucrose crystal at room temperature holds this entire network of hydrogen bonds in a steady, continuous equilibrium, a stillness that is not the absence of force, but the balance of it.
The crystal structure of sucrose positions neighboring molecules at orientations that allow multiple approximately linear hydrogen bonds to form simultaneously. Where the ionic lattice of salt resembles a three-dimensional arrangement of small, powerful, non-directional attractions, each ion holding its neighbors with equal force regardless of angle, like a grid of magnets embedded in a solid. The hydrogen bond network of sucrose resembles something closer to an arrangement of interlocked fingers. Each connection forms at a specific angle between specific partners, with a grip that is gentler than the ionic bond, but constant and present. This directionality shapes the crystal form that sucrose takes, the monoclinic arrangement, a geometry determined not only by the proportions of the molecule itself, but by the precise angular requirements of its bonding interactions with its neighbors. In another layer of this material's behavior, the atomic vibrations within each crystal take their own characteristic signatures. In sodium chloride, thermal vibrations take the form of phonons, quantized waves of displacement that propagate through the lattice in well-defined patterns, the way a single low tone moves cleanly through a long rod of metal, carrying from one end to the other without scattering. Because the lattice contains only two types of atoms and one type of bond, the vibrational spectrum of sodium chloride is relatively simple. The optical phonon modes, in which sodium and chloride ions move simultaneously in opposite directions, like two weights on a balanced beam swinging slowly apart, are fixed at specific, measurable frequencies. Where sucrose requires 129 distinct vibrational modes to account for all its internal motion, sodium chloride requires fewer than 10. The simplicity of the lattice produces a corresponding simplicity of vibration. Sodium chloride absorbs infrared radiation strongly at a wavelength of approximately 61 micrometers. This absorption does not shift between samples or preparations. It is the spectroscopic fingerprint of the ionic lattice, as stable and identifying as the geometry that produces it. The grain on the dish, examined this way, carries its signature invisibly but precisely. The vibrational landscape of sucrose is far more elaborate. A molecule containing 45 atoms carries, according to the principles of molecular mechanics, 129 distinct internal vibrational modes, each one a specific pattern of atomic displacement within the molecule, ranging from the quiet stretch of a single bond to the slow collective flexing of an entire ring structure, like the long, gradual settling of dense timber in cooling air, each part shifting by a degree too small to see or hear. These modes range across a wide span of infrared frequencies. Together, they produce a fingerprint of considerable complexity, dense enough for analytical chemists to identify sucrose unambiguously in a mixture, and sensitive enough to detect the substitution of one sugar type for another at low concentrations. Moving deeper into the structure, the frontier electrons, those at the outermost accessible states of each substance, behave differently under ambient conditions. In the sodium and chloride ions, the outermost electrons occupy complete, stable shells with no low-energy unoccupied states available nearby. Both ions are, in their frontier electron behavior, essentially settled, not reactive, not searching. Their filled shells present a quiet internal completeness, a disinclination toward rearrangement in ordinary conditions. The sodium ion and chloride ion will, in an undisturbed lattice, persist indefinitely in their arrangements. There is no unfulfilled tendency in their electron structure, no available pathway toward further bonding. The lattice rests exactly where it has arrived.
The frontier electrons of sucrose are distributed differently. Across the outermost bonds of the molecular framework, the lone pairs of the ring oxygen atoms, the bonds of the hydroxyl groups, the carbon-oxygen connections at the boundary of each ring. The highest occupied electron state in the molecule is associated primarily with these lone pairs. They are the sites at which enzymatic and acid-catalyzed reactions begin. The glycosidic bond connecting the glucose and fructose rings, the single connection that holds the two sugar halves of the molecule together, is particularly susceptible, because the ring oxygen adjacent to it can absorb and distribute a positive charge that develops as the bond begins to break. This stabilization, which arises from the delocalization of electron density from the ring oxygen into the breaking bond, lowers the energy required for hydrolysis. It is part of what makes sucrose reactive under conditions that leave sodium chloride entirely unchanged. At the deepest level of atomic description available through current scientific understanding, then, salt and sugar represent two distinct organizational strategies of matter. One built on the complete transfer of electrons between atoms, producing charged particles held in symmetric isotropic arrays with equal force in all directions. The other built on the sharing of electrons within molecules, producing complex, asymmetric, directionally bonded structures whose stability is maintained through a network of quieter but geometrically specific interactions. Both produce stable crystalline solids at room temperature. Both dissolve in water. Both have been studied with enough precision that the position of every atom and the frequency of every vibrational mode can be stated in exact quantitative terms. Even if the salt in the dish tells us nothing, we are already aware of how complex a world lies within it. It simply rests, and you, too, can let everything go, clearing your mind and settling into that same quiet. There is nothing quite like lying back and resting comfortably after a long, tiring day. And if you feel the same way, let us continue. There is a particular kind of continuity that belongs to simple, stable matter. A measurable, physical continuity, not something tracked by living eyes or recorded by instruments in a laboratory, but the quiet persistence of a specific arrangement of atoms through time, unchanged in its essential structure, indifferent to everything that surrounds it. Salt and sugar both possess this continuity, though in different degrees and through different mechanisms. And the way each one endures, or fails to endure, across time is the final layer of what these two white crystals have to show. Sodium chloride, in its pure crystalline form and in the absence of liquid water, is among the most durable of common substances. Ancient salt deposits, formed from the evaporation of inland seas hundreds of millions of years ago, exist in geological formations across multiple continents. The Kevra salt mine in Pakistan, the Yelichka deposit in Poland, the massive evaporite formations beneath the North American Great Plains. These deposits contain sodium chloride that has remained chemically intact across geological timescales. The ionic lattice, a structure as orderly and tight as a wall of fitted stones, sealed from liquid water by surrounding rock, has no mechanism of spontaneous degradation. The sodium ions and chloride ions remain in their cubic arrangement, vibrating with the slow thermal hum of the surrounding rock, accumulating small structural imperfections called radiation damage from the natural radioactivity of trace minerals in the surrounding geology, but maintaining their fundamental chemical identity without change. A crystal of sodium chloride extracted from a deposit formed 300 million years ago is, in every measurable chemical sense, identical to a crystal formed last week in an industrial evaporation facility. The lattice structure is the same. The bond lengths are the same. The ionic charges are the same. Time, at the scale of geological duration, has not altered the substance. The long-term stability of sucrose is more limited and more conditional. In its dry crystalline state, sucrose is stable for extended periods. The limiting factor is typically not chemical decomposition, but physical changes, moisture absorption, mechanical stress, and the gradual tendency of the crystal surface to respond to the humidity of the surrounding environment. Sucrose buried in dry, cool conditions, the kind of conditions found in sealed archaeological deposits, can remain identifiable for centuries, though not for geological timescales. The covalent bonds within the molecule are stable against spontaneous thermal decomposition at ambient temperatures, but they are susceptible to hydrolysis in the presence of water and acid over long time scales. In the acidic, moisture-variable conditions of most archaeological sites, sucrose does not survive as an intact molecule across the spans of time that salt survives as an intact lattice. What remains in such conditions are typically the breakdown products of hydrolysis, glucose and fructose, and their further decomposition products, rather than sucrose itself. This difference in long-term stability reflects, once more, the fundamental distinction in bond type. The ionic bond in salt connects particles that have, according to current atomic models, already reached their most stable electron arrangement, a closed, satisfied configuration, like a drawer that has been fully shut, with no open space for outside chemistry to enter under ordinary conditions. The covalent bonds in sucrose connect atoms in a higher energy arrangement, stable enough at room temperature to hold their shape for years without visible change, but accessible to water and acid over long timescales, which can unlock and separate those bonds the way slow moisture gradually loosens the joints of old wood. Given sufficient time, the right conditions, and the presence of water, sucrose transforms. Salt, under equivalent conditions, simply remains. There is a sensory texture to geological salt, to very old salt extracted from deep formations that differs subtly from freshly manufactured salt. Ancient salt deposits often contain trace mineral inclusions, small quantities of calcium sulfate, magnesium chloride, potassium chloride, and other evaporite minerals that were present in the original seawater and co-precipitated with the sodium chloride as evaporation proceeded. These inclusions give ancient salt a slightly different color, off-white, faintly gray, or in certain deposits tinged with pink from trace iron oxide, or in certain geological conditions, what current research suggests may include mineral-associated microorganisms, and a slightly different flavor profile, because the trace minerals contribute ions that interact with taste receptors differently than sodium and chloride alone. Pure sodium chloride is colorless. Of the geological context in which it crystallized and aged. The purity of the ionic lattice itself remains intact. The surroundings have simply left their record in the spaces between and around the crystal grains. Refined white sugar carries no equivalent geological record, because sucrose has no geological origin. Every sucrose molecule found in refined sugar is, according to the established biology of plant metabolism, produced by a living plant within the span of that plant's growing season, a period of weeks to months. The oldest sucrose molecule in a bag of refined sugar is, at most, a few years old, the duration from harvest to processing to packaging to consumption. There are no ancient sucrose deposits. There are no deep geological formations of crystalline sucrose waiting to be mined. The substance exists only because living systems continue to produce it, and it persists as long as the conditions that protect it from hydrolysis and thermal decomposition are maintained. This is not a fragility in any dramatic sense. It is simply a different relationship with time, one that is calibrated to the timescale of biological rather than geological processes. The dissolution of a single crystal of either substance in a small amount of water is perhaps the most quietly complete transformation either one undergoes under ordinary conditions. When salt falls into water, it disappears. Imagine a crystal that took years to build vanishes within seconds in a small amount of water. But if you evaporate the water, the salt comes back as if nothing ever happened. This reminds me of certain wild plants. Some wild plants, even when pulled out from the root, begin to grow again, because they have deep roots, and through those roots they are able to regrow. I compare the memory of salt to this. Even if this comparison is not entirely related, I think you understand what I mean. It will arrange and rebuild the crystal, face by face, ion by ion, exactly as it was before. A crystal of sucrose dissolving in the same drop of water is, chemically, less reversible under ordinary conditions. The water molecules form hydrogen bonds with the hydroxyl groups of the surface sucrose molecules, pulling them free from the crystal lattice and into solution as intact molecules. The crystal retreats and disappears, just as the salt crystal does,
but the sucrose molecules in solution, being large and complex and surrounded by a dense shell of hydrogen-bonded water molecules, do not spontaneously reorganize into a crystal unless the conditions of temperature and concentration are very carefully managed. Evaporate the water from a sucrose solution too quickly, or cool it too rapidly, and the result is amorphous solid, the glassy, non-crystalline form of sucrose that lacks the geometric order of the original crystal. The molecule is intact, but the long-range order that made it a crystal is gone, and recovering it requires patience and controlled conditions. The crystal, once dissolved, does not simply rebuild itself the way salt does. In this sense, the two dissolutions, salt into water, sugar into water, represent two different relationships between structure and reversibility. Salt dissolves and can be recovered, unchanged by simple evaporation. Sugar dissolves and can be recovered in crystalline form only under conditions that allow the molecules to find each other and orient correctly before the solution solidifies. Both dissolutions are quiet, both are complete, both leave behind a clear liquid that carries no visible trace of the geometry that existed before. The transformation is invisible from the outside. Only the careful measurement of physical properties, the way a solution conducts electricity, bends polarized light, or changes how quickly it slows a beam, reveals what is present and in what form. This is where the narration of these two white crystals comes to rest. Not at a conclusion, because the chemistry does not conclude, but at a point of sufficient stillness. The salt and sugar on the kitchen counter remain where they are, organized and patient. Their structures are measurable. Their behaviors are predictable within the ranges that current scientific understanding can describe. Their differences in bond type, in crystal geometry, in thermal behavior, in osmotic efficiency, in long-term stability, are real and precise, documented across more than a century of careful crystallographic, spectroscopic, and thermodynamic study. And their similarities, two white crystalline solids sitting quietly in their dishes, waiting for whatever comes next, are real and equally worth noting. And we have now reached the end of our video. I hope it has helped you drift into a peaceful sleep or simply to unwind. If you enjoyed the video, leaving a like and subscribing to the channel will help more people find their way here. Until next time, good night. See you in the next video.